In this video, we'll talk about how gliders fly and introduce the basic principles of flight. You've almost certainly been lied to about how planes fly. You may have seen this diagram of the 4 forces required for flight. But in a glider, there's no engine and therefore no thrust. And this diagram is clearly wrong because the forces don't balance. Imagine someone on a skateboard. Here, the weight of the skateboarder is counteracted by the reaction from the ground, but the drag or air resistance will gradually reduce the speed until the skateboarder stops. Now imagine a skateboarder on a slope. As before, the weight is acting vertically down, the drag is acting in the opposite direction to motion, and the reaction force is perpendicular to the surface. If we resolve these forces parallel and perpendicular to the direction of motion, we can see that part of the weight is pulling the skateboarder downhill and overcoming the drag. Therefore, the skateboarder is able to maintain a constant speed as long as he continues on the same slope. A similar concept applies to a glider, where it must always fly slightly downhill, trading off height to maintain speed. And here we can see the balanced 3 forces acting on the glider. If the glider is always going slightly downhill, we can define the glide ratio as the distance forward the glider can fly for each unit of height lost. One of the features that sets gliders apart from other aircraft is that they have much higher glide ratios, and therefore they can travel much further for each unit of height loss. But how is the lift generated? Well, the wings of a glider work exactly the same way as any other aircraft, but how wings work is often explained so poorly that it becomes factually incorrect. The true explanation of lift is that it is the consequence of solving the Navier-Stokes equations for a fluid flowing over an aerofoil. But as you can see, these equations are quite complex. For a simplified explanation, imagine some air flowing from right to left. The lines here, called streamlines, represent the motion of the air. Now we've inserted an object into the airflow. In a perfectly frictionless world, the airflow would wrap round the object and return to its original course. To make the airflow turn, there must have been a force acting on it. This force comes from a pressure gradient, with the lower pressure on the inside of the turn and the higher pressure on the outside of the turn. Therefore, around the object there must be areas of low and high pressure. Now imagine a thin, flat plate in the airflow. When it's perfectly parallel to the airflow, the air goes around it with no effect. If we rotate the plate, we call the angle between the airflow and the plate the angle of attack. Introducing an angle of attack forces the streamlines to curve around the plate. This creates an area of low pressure above the plate and a small area of high pressure below the plate. This pressure difference creates lift. Increasing the angle of attack forces the streamlines to curve more, increasing the pressure difference and thus increasing the lift. In the real world, with friction, the streamlines are not able to turn tightly enough to flow round all shapes. This results in flow separation. When the flow separates, the area of low pressure above the wing is significantly reduced, and therefore the lift is also significantly reduced. This is known as the stall. Most aircraft don't have flat plate wings. That is because the aerofoil is a better designed flat plate, which for the same angle of attack will give you more lift, less drag, and has a nicer control of the stall characteristics. The increased thickness allows you to put structural elements in which support the wing.